Recently, we've seen several examples in which when we want to do a probability calculation, compute a probability, compute an expectation, that kind of thing, it's helpful to consider simpler random variables and then build up. So we saw an example of this idea when we did the law of total expectation, when we considered simple probabilities in different scenarios, and then combined those scenarios weighted according to the probability of each one. We did another case when looking at the expectation of a sum of random variables. Easier to look at the sum of expectations. So there's all these cases where, in order to break down a problem, it's helpful to express it in terms of very simple pieces. And what we're going to do here is introduce kind of the simplest pieces of all and show how we can use them in some helpful probability calculations. So let's introduce indicator random variables. So a random variable that we'll call x is an indicator random variable of an event A if it's the case that x is equal to 1 whenever A occurs and x is equal to 0 otherwise. So a quick example of this. A quick example. Bernoulli random variable is an indicator for a coin coming up heads. That's one way to think about it. The Bernoulli random variable has value 1 if the coin comes up heads and 0 otherwise. Here's a slightly more complicated example. So what we'll do is we'll roll 3 die and we'll sum the result. We'll add it together and we'll set x equal to 1 if the sum is larger than 14 and x equal to 0 otherwise. So this is like passing a check in D&D or something like that. So if we look at the outcomes here, and then the values of this indicator random variable, an outcome, maybe we roll a 3, a 1, and a 4. The sum is 8. Our indicator has value 0. Maybe we roll a 6, a 5, and a 5. Total 16. Our indicator has value 1. Two more examples. Here's a 1, 5, 3. No good. And that only adds up to 9. And then 2, 6, 6. That is not strictly larger than 14, it's only equal to 14, and so that one's a 0 as well. So our indicator random variable, it has value 1 whenever something happens, and value 0 whenever that thing fails to happen. In this case, the event is the sum of 3 die being larger than 14. So let's look at an application of this. This is just an example of how we would compute the values of an indicator random variable given some outcomes. But this actually can be a tremendously powerful tool. So let's look at an example where we're going to use this effectively. So let x be a binomial random variable. We've seen the binomial distribution recently. Let x be a binomial random variable with n trials and success probability p. What's the expectation of x? So in other words, if I flip n coins, each of which has probability of heads equal to p, what's the expected number of coins that will come up heads? So let's try to do this two ways. So attempt 1, I am going to use the definition. And when I do this, okay, I'm going to get the expectation of x is going to be equal to, okay, so the definition is that k needs to range over all possible values. So that's 0 to n. I could have 0 coins come up heads, or I could have n coins come up heads, or anywhere in between. Value k of the PMF of x evaluated at k, which is equal to the sum from k equals 0 to n of k times n choose k times p to the k times 1 minus p to the n minus k. And if you're looking at this sum, you might look oh dear, how do I do this sum? I don't know how to evaluate this sum. It's not something we've covered in class. It's not something that you would cover most of the time, and it's going to be unpleasant. I don't actually know how to compute this sum. So in a way, I am stuck. I don't know what to do. Attempt 1 is not going to work for me. Let's now try attempt number 2, where in this attempt, we are going to make use of indicator variables. So in particular, I'm going to say that x is equal to the sum from I equals 1 to n of xi, where xi is the indicator of the event that coin I comes up heads. So in other words, we think about flipping n coins, and we can ask specifically about the a specific coin, like coin I, coin 1, coin 2, coin 3, coin I, coin n. What's the probability that that coin comes up heads? What we know is that each of these xi's is relatively simple. In particular, each one is a Bernoulli random variable. And its expectation is just like any other Bernoulli random variable. If the success probability is equal to p, the expectation is equal to p. We just derived that not too long ago. So by linearity, we know that the expectation of x is equal to the expectation of the sum of all the little x sub i's, which by linearity is equal to the sum of all the expectations. Each of those expectations is equal to p, and there are n of them in total. So my result is n times p. This actually matches something that we saw previously. So previously we derived, if I flip a fair coin that has probability of heads equal to 1/2, if I take that fair coin and flip it 3 times, the expected number of heads I'm going to get is 3 times 1/2. 3 is the number of flips, that's my n, and p is 1/2, that's the probability of heads. So using indicator random variables and properties of expectation like linearity, I was able to avoid really complicated calculations that I actually wasn't able to do in favor of doing simpler calculations using simple rules. I just needed to bring in indicator variables and then remember some of my properties for expectations in order to make my life simpler.